one of the thing that I want to emphasize is that even when h bar is equal to 0, there is very interesting mesoscopic and nanoscopic physics, and it's not only to reduce scale, but really it has to do with very interesting statistical physics that exist only in the meso scale. So maybe, so Alex, maybe if you want to discuss things, we can discuss this also, because I don't share your views on that. So first of all, well, if they give me more time, we can start now. In any case, the first thing that I would like to say is that I would like to acknowledge my postdoc, who was also a Nano Fellow, and this is a nice occasion to acknowledge also the Nano Center for the support. Shinkun Man, which you can see him here, you know, in the background you see a little bit of the Eiffel Tower, and this has to also say that our collaborator in this work were people from the CEA, the Atomic Energy Commission of France in Saclay, and they include Henri Orland, a very good friend of mine with whom I'm collaborating for many years on the theory, and the experimental group of Jean Dayan and Patrick Guénoun, who gave us some of their data, and we work with them as well. The outline of the talk, it's not a very long talk, so the outline would be, I would like to introduce some of the nanolithography and block copolymers, assuming that you don't have extensive knowledge of that. And then I will go and show you some of the results on surfaces and polymer films, especially in the relation of nanostructure and nanoimprint lithography, which is a topic of what I'm doing. And if time permits, I also would like to show some result on the free interface, the interface between the polymer film and air. So let me start by a very schematic view of optical lithography. So this acts as a motivation. I'm certainly not an expert in that. Basically, optical lithography that you use in microelectronics is very similar to lithography that is used by painters. You start by producing a very expensive but only one sample, which in this case is called the photomask. You take the substrate on which you want to imprint the pattern that you have on the photomask, and you coat it with a photoresist. This is actually a polymer that is sensitive to light, so when it's interacting with light, it will change its chemical composition. And you shine light, UV light, through the mask, and you change the properties of the photoresist film, and then by some chemicals you remove away either the positive, what is called the positive resist, or the negative resist. You remove away one of the two components, and then by further etching you imprint permanently the structure that you have on the photomask into the substrate. So this is, in two words, the process of optical lithography that is used in microelectronics. So as I said, you have one copy that is very expensive, the photomask, and then the advantage is that you can, by rather cheap chemical, you can repeat this process on many, many silica wafers. So this is the state where we stand now. Present technology uses 193 nanometer optics, so this is in UV light. And what you can see here is a reduction in what is known as the technological nodes, the smallest feature of the pattern that is pre-decided by the industry, which went down from 10,000 nanometers all the way to 32 nanometers nowadays. So this represents a factor of 300 in 400 years, and this is directly related to the Moore law, the law that states that every 2 years or so the number of transistors doubles. So the semiconductor industry have this special consortium. It's called the International Technology Roadmap, And this consortium, which I think encompasses many of the people that are involved in the industry and in the research, they decide about the future nodes, to which pattern we are going, smallest pattern we are going to go. And this is what you can see here. So in few years, the projection is 22 nanometers from 32 nowadays, and then 11 nanometers in about a decade. So of course, this involves huge amount of technology, and there is of course some projection in that. We are not sure that we are going to get there, but basically this is already pushing the limits of present day technology that is based on this UV light. So people try to find many other types of lithography that can produce smaller and smaller features. And I list here some of them, ranging from X-ray lithography to magnetomask lithography. All these techniques are techniques that people work on nowadays in order to reduce the smallest feature possible so that you can condense more and more transistors into the chip. So I will not talk about any of this method. I will talk about actually another method that people are trying to use. It's still quite in a preliminary stage. This method is basically a bottom-up method, and it uses the self-assembly of functional polymers. It's a particular type of functional polymer called blockopolymers. And this is what I meant before when I said that there is very interesting physics that is really specific to the nanoscale of these blockopolymers, and I hope that I will be able to convince you that this is indeed the case. It's not just scaling down, but actually this is a bottom-up approach where you use a self-assembly of the polymer in order to create patterns and to use them according to your wish. So this is the type of thing that people are thinking of. So these are actually real experiments done on a silicon wafer with some dot pattern. And the cylinders here are produced from blocopolymer. I will explain it later. And depending, you see on the angle and some other parameters, you can get this interesting feature, defectless, with no defect feature on the pattern surface of the cylinders of blockopolymers. And the dream is that we can use this type of self-assembly, namely cylinders that are produced by themselves, in order to replace some of the processes that require nowadays the photomask. And you can see the scale here, dozens of nanometers. This is the scale, the length scale characteristic to polymers. Okay, so that was the motivation. Now let me go and tell you a little bit about blocopolymer, assuming that not everybody knows about them. We heard yesterday a talk by Roy Amir, who showed interesting application in the biomedical application to blockopolymers. Basically, blockopolymers are polymeric chain, flexible and long polymer chain that are not formed out of one monomer, but they are formed out of at least two monomers. Each of them creates a long block, and those blocks, like here, the polystyrene and polyisoprene, are linked together covalently. So basically here we have a lot of richness in the system. Even if it's just a simple diblock of polymer, the richness comes about because the two blocks don't like each other. They would like to phase separate. And then you have a competition between the fact that they are linked together. This is a covalent bond. It's unbreakable at regular temperature up to a few hundred degrees. And then the two blocks try to avoid each other so they can at most create some microphase separation. So you create in equilibrium domains in the nanoscale of blocks that are rich in one of the component and blocks that are rich in the other component. And of course, because this happens in the nanoscale and it's happened in a self-assembly way, the hope is that one can use those type of polymers as functional materials in nanolithography. They are used in many, many other applications, both in bulk and also for their nanostructures. So this type of frustration that you have, I sometimes like to call Shualei Shimshon, because you can see that it's like the foxes of Shimshon, of Samson, that were bound together, and they try to avoid each other as much as possible because of the fire, and this is the same thing. So you try to create, given this bond, the best possible structure with the constraint that you have in the system that you cannot remove. So let me, for example, show you why with some such simple consideration, this is backed by quite sophisticated theory, why with such simple consideration we will get at equilibrium a lamella phase. A lamella phase, as you can see here, is just a stack, a simple stack in one direction. You can find this periodicity by using some X-ray scattering, and this periodicity is in the tens of nanometer range, and it's very well defined in the system. So why is that so? As I said before, the two blocks do not like each other. It's like oil and water at a large temperature range, so they have some interfacial tension between them that they will try to minimize. However, as they try to phase separate, the red and the blue trying to go away, you remember that they are linked together, so they cannot go away too far. What does it mean? It means that as this domain tries to become longer, the chain will stretch. A stretching polymeric chain, it's meaning that you are losing entropy. You are losing the chain configurational entropy, and at some point these two things will balance, and the balance is written here in terms of the scaling law, where L naught is depend on the interfacial tensile gamma and on N, which is the size of the chain. In practice, it looks like this. This is a TEM, a transmission electron microscopy, which is a cut through a lamellar phase. And you can see that there are, of course, a lot of defects. The system is rather viscous. It's a melt. But what you also can see is electron density contrast between the two blocks. And the sizes here in the tens of nanometer scale is rather well preserved throughout the system. The lamella is just one phase. It's a phase that I'm going to discuss mainly, but there are a whole zoology of very nice phases. Even for diblock copolymer, you have several other phases. This is a gyroid phase. It's a bicontinuous phase, which means that both the A and B percolate throughout the system. It has a cubic symmetry. And when you also do something a little more complicated, you don't use a diblock, but a triblock, depending on very few parameters, which is the relative length of the A, B, and C blocks, and on the mutual interaction between the three pairs, you can get a wide variety of phases. As you can see here, this is a lamella, but then you get cylinders and spheres and embedding of one into the other, very, very complex phases that are obtained at equilibrium. So you don't have to do anything. You just take the chain, put them at the right temperature range, you determine their length, and you get a very nice phase like that. In terms of the phase diagram, the triblock is very complex. I'm showing here only the diblock. The diblock depends only on two parameters. It's amazing. It really depends only, to a very good approximation, on the molar fraction of the chain, namely the relative length of one of the block in the chain, so that, let's say, 0.5, F equal 0.5 would mean a symmetric chain. We mainly will work with symmetric chain. So we are on this line here. And then the parameter here is a product of the length of the chain and chi. Chi is, in polymer physics, is the famous Flory parameter. It's a parameter that is related to the surface tension between the two blocks. And it basically tells you the chemical compatibility between the two blocks, so that since it's inversely proportional to temperature, you have here at high temperature, in practice it can be about 200 degrees Celsius, you have here a disordered liquid phase. As you cool the system, you increase this chi parameter, n times chi parameter, you go into the lamella phase, and on the sides, the asymmetric block copolymer will have other type of structure and symmetry. It's important to know that on this phase diagram, I can only change temperature once the system is determined. I can, of course, create many different systems with many different Fs, but for one system, one F, I go on this line here, so I can go from the disorder to the lamella if I'm in the symmetric case. Okay. In terms of theory, so there are several types of theory. I will just very briefly discuss one of them, which is the one that we use in our study. It's called the self-consistent field theory. It's a mean field type of theory that is based on the seminal works of Sam Edwards in the 1960s. And basically what Sam Edwards was able to understand and to show at that time is that polymer physics is very much like field theory in quantum mechanics. The line here that denotes the length along the polymer starting from 0 and going all the way to the total n, t, is actually like, in some sense, like time in a path integral in quantum mechanics, just that this time is imaginary. So the important quantity is this Q. Q is basically the probability of finding the monomer along the chain at distance t from the beginning at a position r, while I'm holding the end point of the polymer at another position u. So it's some type of a conditional probability. And then if I'm integrating over all possibilities of having these endpoints in space, I am getting this little q, which depend on t and on r. Now, this little q satisfies something that looks like a Schrödinger-like equation, or if you want, a diffusion-like equation, where t, as I said, is like imaginary time in quantum mechanics. And you also can see that the chain is not free, but it's coupled to an auxiliary field omega. What is this field? Here comes, it's very similar to other types of mean field-like theories in condensed matter. This auxiliary field is a field that is coupled to the fact that I am taking one chain embedded in a soup of all the other chain, and I'm replacing this soup of all other chain by some type of a mean field. So I have this auxiliary field. The auxiliary field will be determined by the concentration of the local concentration of the chain, and basically I do it in a self-consistent way so that I am solving this equation for a given omega. I'm finding the concentration, and then I'm plugging it back in such a way that I would like to get the concentration that is constrained from the beginning. Now, this was, as you see here, there is no block copolymer here, just for simplicity. For a block copolymer, I really would need to have two different propagators along the chain to separate the two different chemical species along the chain. And this, of course, can also be done so that the concentration phi is not the total concentration, but is the relative concentration of the two blocks, and that, of course, varies in space. So this is something that we do. Okay, so let me show you now some of the basic sign and application of thin film. So far I was talking about block copolymer in the bulk. So thin film, I would like to start with a very nice application done at MIT about 10 years ago. And in this application, the block copolymer, which is here, you see the two different species. These are little dots, little spheres of one block copolymer embedded in other, and this acts like the mask, like the photomask. The process is a process where you see you have the silicon wafer, and it's coated with several layers of metal, and then via standard procedure of bombarding the surfaces with ion and etching it, you can imprint the structure of the block copolymer all the way into the cobalt layer, and in such a way that you produce, on this scale, you can produce an array of cobalt dots, and cobalt, of course, is magnetic. So that is a nice way of using block copolymer as a template. In terms of the theory, what we need to do is we need not only to take into account the bulk of the block copolymer, but the interaction of the block copolymer with the surface. We model the surface in terms of some surface preference field, which I call U. Since there are chemical pattern on the surface, I would take a function U that will depend on the position on the surface and will couple it to the local concentration of the block copolymer at the surface. So I have to add a term like this, and of course I need to minimize the free energy, and I minimize it within the constraint that I was explaining. So this U is just the relative preference of the surface that is chemically interacting with the two blocks. Okay, and usually if you take any surface like silicon and two types of block of polymer, polystyrene, PMMA, which is a standard type of block of polymers, the difference of the bare silicon with the two is about 10 to 15% of their mutual interaction. So let's start first by looking at a surface that is just coated and prepared in a way that it has a uniform preference toward one of the two blocks. How do you do it? As I said, silicon has some preference. In many cases, what you can do is you can coat the silicon with a self-assembly monolayer, and then by oxidizing in various degrees the monolayer, by just shining it with ultraviolet light, you can really tune this interaction parameter U to your desire. So this is here shows you a behavior diagram. U is on the vertical axis, and the thickness of the film of the block of polymer on the horizontal axis. You control the thickness by the spin coating technique, which is a technique where you spread by spin coating a block of polymer from a volatile solvent. Then the solvent evaporates, and this thickness is predetermined. So what you can see here is that depending on the value of this thickness, measured in units of the natural length, L0, the periodicity of the block of polymer, and in terms of the strength of the surface interaction, you get that either the parallel or the perpendicular phases are stable. Clearly, if U prefers the blue block, if U is large, it would like to have the U touch the surface, so you are in the parallel configuration. Of course, I'm avoiding here the discussion of defects, which are abundant, but just in terms of energetics of these two phases, while you see that when this thickness is not commensurate with an integer number of layers, or more carefully with an integer number of half layers because of this BA type of periodicity, then you will stabilize the perpendicular phase, because here you see you don't have any constraint on the length. So we understand, and also in terms of the experiment, people understand how to create surfaces that will prefer, for example, the perpendicular phase. So the perpendicular phase in terms of the application is the desired phase. Why? Because you see, when you look on the film from above, you do see the contrast between the two blocks. So if you think about some type of a selective etching of one of the two blocks, you really want to have the whole block of polymer aligning perpendicularly so that you can etch away, for example, the red and leave the blue. This is a real top view taken by AFM by the French group, and I'm not sure if it's seen so well, but if you look at it with less light, you will see that it actually looks like a fingerprint. So it's a phase that stands up, and it has lots of defects in it. It has lots of defects because the way that the block of polymer is produced, as I said, it's produced by spin coating. There is a lot of shear in this production, and it's a viscous material even at a temperature between 100 and 200 degrees Celsius, so that any types of this defect will be extremely hard to anneal unless you do something special. This is a result from our self-consistent field theory, and you can see that in the result as well, the block of polymer is standing up, but you do have these defects in the layer. They are not just nicely parallel layer. And one of the problems is that you don't have any control on this defect. For the application, you really need to anneal them away. You really need to get a control and a well-defined, oriented, in-plane oriented block of polymer in this perpendicular phase in order to be able to advance in this line of thought of doing application. So the main question that people addressed in recent years is how really to align the block of polymer in this perpendicular phase, how to avoid the defects. So there are several groups and several different ways. One of the ways used actually photolithography, where you are imprinting on this imaging layer, which is sitting just above the substrate. You are imprinting patterns chemically. The thickness of the pattern is D, and those patterns interact differently with the two blocks. So basically, they are acting as guiding lines to the blocks, and when you deposit the block of polymer film, and it is in the perpendicular phase, they will help guide the lines parallel to it, as you can see here. So what you can see on the left, this is a picture without this procedure. You see block of polymers that are standing up, but you have lots of defect. Here, this is a procedure where the block of polymer are very nicely oriented, parallel to those patterns. But the problem here is that in order to induce such a nice ordering, you need that the stripe width D will be more or less equivalent to L naught, which is the natural length. So in some sense, this is a circular type of argumentation, because you tried from the beginning to reduce or to avoid using the UV lithography, but here, in order to get it, you need it again. So people try to think about some other techniques. The other technique is seen here. It's called graphoepitaxial technique. And in this technique, what you do is, beside playing with the layer adjacent to the substrate, you are also creating some pillars on the silicon wafer. So you create a topographical guiding pattern that will help guide the layers in between. And as you can see, this is, for example, a preferred orientation. It depends on the interaction between the various components with the block of polymer. And in this case, which you can see here, this is the top view of electron microscopy. You can see here that indeed you are able to guide the block of polymer in the perpendicular phase, because you are looking on it from the top. And there are several layers that you are able to guide. So the thickness here of the width here can be 10 or so, 20 times the natural periodicity of the lamellae. The problem with such a technique, if you think about application, is that you would need to modify the wafer, each of the wafer to start. So it's not something that you can do once, like in a photo mask, but you really need to treat the wafer, and again, this would cost quite considerably, and it's not something so nice to have. So again, people try to think about some other techniques. So this is the technique that the group in Saclay was using. They were I think they were the first to use it for block of polymer, but there are other groups that use it for homopolymer. So the idea here is rather simple. What you do is you start with the silicon wafer, which you pacified, so that this preferred interaction is pacified by the self-assembly monolayer. So you have a perpendicular phase of block of polymer, but it's disordered in the plane. Then you use a mold. And the mold is like a stamp, a rubber stamp that you create once. It's expensive to create, but you create it once. The mold have a small preference towards one of the two blocks. And you press the mold onto the block of polymer film, and you heat it up so that it's in the liquid lamella phase. It's not. It's above the glass transition. And then after you release, hopefully, because of the interaction of the walls of the mold with the block of polymer, you will get such nice arrangement of the block of polymer. And the advantage here is that this mold is produced once, and then you can stamp it maybe 1,000 times. So there is a clear advantage here. It's not that there are no problems, but at least there are some advantages over other methods. So this is how it looks in reality. This is the surface. This is some block of polymer film, and you press the mold, and after some time, hours, when you release the mold and you cut through the system and you look with the electron microscopy, you find that the arrangement is quite nicely here, perpendicular here to the layer, but if you note close to the wall, the arrangement in some places is parallel to the wall or perpendicular to the down surface. This is one way of doing it. You see the film is disordered. It's disordered because I told you that you are spin coating the film, and then it takes time for the lamella order to come about. If you wait and you pre-anneal the film, and you can see here the beginning of a lamella order, which is in this case parallel to the surface, you do the same procedure. You see that in this case, the lamella will be perpendicular to the bottom surface or completely parallel to the walls of the mold. And this is only preliminary study, but it's showing how much important is the initial condition of the film. The fact that you were in the disordered phase or you were already in the pre-annealed phase makes a lot of change. And of course, it's also, what I'm not discussing is the film rheology. The film rheology, the flow of the film, the microflow as you are pressing and the polymer film is flowing away, is extremely important as well, because the flow also can act as an ordering field besides the surface field. So we try to mimic this in our theoretical study. What I'm showing here is a difference of different type of temperature quenches. This is a quick temperature quench. You start from the disorder phase and you quench immediately deep into the lamella phase. And as you can see in this case, we are not reproducing a nice perpendicular phase, but we are rather reproducing a mixed phase of perpendicular phase here and a parallel phase here. You see red, blue, red. This is just like one layer twice red, blue, red. So it's two layers of the block copolymer. And the reason is that the walls of the mold have a preference towards the red, and if you do it fast, this preference will penetrate in this horizontal region, and you will get stuck into this mixed, undesirable state. If, on the other hand, you do it slowly, you quench, you change the temperature in small steps, you go through the transition from the disorder to the lamella, you actually can, with the same amount of U is not large, you can get a perfect perpendicular phase. So the other thing is that I would like to show you to what extent we can guide the lamellae in this mold. So this is now the thickness here is about 20 L0, taken in this way. And both in theory and in the experiment, we still can align them very nicely. I want to show you a blow-up here. So you can see this is a wall, and this is a block copolymer layer that are really very nicely oriented close to the wall. This is a three-dimensional studies where it's much more extensive and the simulation box is smaller. But you can see here the difference between the defect in the flat surface case with the very nice order due to these fingers, the black fingers that are part of the mold that is inserted. If we make the width here larger, about 40 L0, we are going to lose again the perpendicular phase. This is both seen in the simulation, again in the middle away from the wall. You recover the parallel phase because of this problem of competition between this wall trying to arrange things in the parallel way and the vertical wall which try to arrange it in the perpendicular way. And actually this is seen also in experiments where the effect of the wall persists but only to some degree. So the three important findings of nano-imprint lithography, both from experiment and theory, is that you need to change the temperature in a gradual way, otherwise you are going to get trapped in metastable state. The thickness can be large, but of the order of 20 to 30, but not too large. And the other thing is that the preference field on the mold should be small, about 2%. If it's too large, again, you are going to destroy the perfect perpendicular order. So how much? No, nothing. Okay. So I will just, maybe I will just show you one result of the free interface problem. The problem here is much more complex because we also want to understand the self-determined interface between the film and air. So you see this interface is like an interface between a system that phase separate, the block of polymer phase separating from the air, and we treat it in a way that we introduce another degree of freedom, which is like a bed solvent, the air. And I will just show one result here. Depending on the thickness, you can get either the flat interface as before. So this is the case where the thickness here is commensurate with an integer number of layers. Or in the case where the film thickness is not commensurate, if you have a middle pattern here that prefers the parallel orientation, you are going to get a real droplet. And the important thing is that this droplet comes about because you are constraining the volume of the film. It agrees with the Young equation for the contact line, and this is still work in progress. So let me just skip that and maybe just say that in terms of the block of polymers, as they are very interesting system that has specific properties, structural properties in the nanoscale. In terms of the nanolithography, I think it's still, there are quite a lot of challenges that are written here, and we are still working on it, and in experiment people still work on it. It's not clear how good this technique will be, but it has quite a number of advantages that it will be interesting to further explore. Thank you very much.
Since, of course, I'm not in this field, I got a bit confused. Which of the three-dimensional organizations that you showed in your talk are a result, in principle, of a minimum free energy, and which are imposed by imprinting and therefore do not correspond to a predictable free energy minimum? For instance, the beautiful picture you showed early on about three-dimensional organizations, I don't know if it's easy to bring it back or not, which were a compromise of entropy of minimizing avoiding minimum entropy and at the same time avoiding repulsion. Are these predictable structures? Can you tell which structure it is, and in which cases the structures are not predictable but are basically constrained by the imprint?
Okay, so that's a good question, and it doesn't have a simple answer. In general, also in the way that you look on the way that the films are produced in experiment, they are not always in their equilibrium state. So basically, in terms of the theory, what we try to do is we try to get the minimum of the free energy of the system, but imposing quite a number of constraints. Due to the fact that you have so many constraints, you can easily get trapped in metastable state. So we try to do all sorts of tricks to be sure, to some extent, that we are not getting trapped into this metastable state. Of course, if I will find that two states will have, one will have a lower free energy than the other, I will know that the other has a better free energy. But it's not a technique which I can assure that I'm always in the best minimum given the external constraint.
Can you just summarize the comparison between theory and experiment regarding the predicted packing pattern? How close can you come to experiment by predicting what would be the structure?
So I think that in simple situation, and I showed it for example, for the mold, I can predict in rather semi-quantitative agreement. I'm sorry? The ABC case we didn't do, and it was also not done in experiment. We just did the AB case. So for the AB case, I can predict with this gradual temperature annealing, I can predict some of the structures, of course, with some limitation on the size.
Okay, just a quick question. Can you think about, or maybe it's not possible to think about a way where you impose a kind of a long-range gradient. For example, gradient of the surface or a gradient of temperature to align the lines along the to get a sort of alignment along the direction of the gradient. So instead of
you are talking about using a gradient in order to orient the films.
Yes.
Yes, and actually this was done. So it was done by several groups in Japan, and actually, for example, so it was done as a ordering fields. And not always it's possible to other type of in some sense gradient are electric field, gradient between potential also was done. It's not always applicable to all situations, but you can easily orient block copolymer film in electric field using, for a film of 10, let's say 1 micron, you can use like 100 volt, and it's easily oriented due to the dielectric difference between the two blocks. You can decorate one of the two blocks with some material in order to enhance the dielectric discrepancy between them as well.
All right, thanks again.